Okay? So the energy has gone down quite a bit because it gave its charge to this. Where did that energy go? Into the heat, into the wires. When we connected wires here, okay, it went into the energy loss as you are delivering, as this is delivering charge to them, the energy loss of the wiring, okay? So, what's the percent loss of energy? The initial energy is 150 minus the final over the original. So 150 minus 34.625 divided by 150 times 100%, 76.9% loss of energy. Okay? Now, what would have happened if instead you had this situation? If you combine the three microfarad like this, is 6 and a 4. And of course, you can make more intricate circuits that you want. You can have more capacitors, and you can make this problem as complex as you want, right? So what's going to happen now? Well, now the combined capacitance is going to be less than either one, right? 1 over 4 plus 1 over 6 equals 1 over C. And then you have here 6 plus 4 is 10 over 24. C is equal to 2.4 microfarads. So their combined capacitance acts like a 2.4 capacitor. So it's like taking a 3, connecting it to a 2.4. Then you go through the same arguments. The voltage of this is going to be, this is Q1, Q2. So Q1 over 3 is equal to Q2 over 2.4. And then the sum of the two is still equal to 30. Okay, and then this one is going to be 72 is equal to 5.4 Q2, and then 72 divided by 5.4. So Q2 is equal to 13.333 with a repeating 3 basically. And then Q1 is equal to 30 minus the answer, 16 with a repeating 6. Okay? So that means the charge of this guy has not dropped as much. Okay? It's only given this guy 13.3 microcoulombs. Okay? What's the charge of each of these? Well, since they're in series, it's the same. So the charge of this is 13.3, 13.3, 16.6. Okay? So what's the voltage of each now? The voltage of this guy here is going to be, remember, V is equal to Q over C, right? So you're going to have 16.6 over 3, 5.5 repeating 5s, okay? This is going to be 5.5 volts. That means when you connect it to two capacitors in series, since the capacitance is less than either one alone, it has less effect on the original capacitor. So its voltage goes down to 5.5 repeating 5s. The voltage of this, let's call this one V1 here. This one is V2. So it's going to be 13.3 over 6. 2.2 repeating 2s, right? And then what's the voltage of this going to be? 13.3 over 4, right? It should be such a number so that when you add it to it, you get 5.5, right? Because these are in series, so their voltages add up. So it's going to be 3.3 volts, then with the repeating threes, and then when you add them, you get that. Okay? So what's the total energy of the system now? Okay? U total is equal to, I could say 1/2 times 3 times the 1/2 times the capacitance times the voltage, 5.5 bar squared, plus 1/2 times the capacitance times its voltage squared, which is this is 6, and then this is the voltage is 2.2 plus 1/2 times 4 times 3.3 bar squared. Okay, and I already done this calculation, and then the calculation for this one came out to be 83.3 joules, okay, microjoules I mean. So the total energy at the end is more than it was in parallel. So the percent loss of energy, 150 minus 83.3 over 150, the percent loss of energy is 44.4%. So you can see this is kind of a generic example of cases where you charge a capacitor, you connect it with something else, and then what happens to the situation after that. Thank you.